let's define this idea of invertible. So we've now defined the reverse of a set of pairs, or of any set, just the reverse, just flipping pairs around. But the idea of invertible has a little bit more to it. So you have to be talking about a function to begin with, and we say, so assume f is a function, and we say f is invertible if and only if, when you take f and reverse it, which is something you can always do, you can always reverse all the pairs, that is a function. So here I'm defining this predicate, is invertible. To say f is invertible is to say the reverse of f, which is always something you can examine, whether f is invertible or not. The reverse of f is a function. So remember, is a function is this. It means these two things. Is a set of pairs. Okay, that's automatic. The reverse of something is a set of pairs, but mainly this. This condition. So this condition has to hold for the reverse of something in order for that thing to be called invertible. Then, in this situation, we would call f reverse the inverse of f. So here I'm defining this terminology, the inverse of f. So the reverse of f, which, by the way, I don't know if that's standard terminology. It might not be. But the inverse is definitely standard terminology. So the reverse, I don't even remember now. It's quite possibly something that I made up. But the idea is around, of taking a set of pairs and flipping around all the pairs. The reverse is something you can always consider, but you can only call it the inverse if what you were looking at was a function and the reverse turns out to also be a function. Then you can call it the inverse. Okay, so this is the situation where I feel more comfortable writing it as f to the negative 1 power, because now it matches up with kind of the algebra way of denoting things. Okay, let's just think about this visually a little bit. So assume x, y, and z are distinct, and let's say capital X is this set consisting of x, y, and z. So let's talk about functions from capital X to capital X. They don't have to be, but let's just do that for now. Let's just make one up. How about a function that flips x and y and sends z over to y? This is definitely a function, right? Remember, for it to not be a function in the picture, you would have to see a situation like this, a picture like this on the left side, right? Looks like this is a function. So here, if this is f, this is this list of pairs. It consists of x, y, y, x, and z, y. Now, what's f reverse? Does f reverse exist? This is something, people sometimes ask, does the inverse exist? Does the reverse exist? Yeah, the reverse exists. Just flip these around, right? yx, xy, yz. The reverse exists. Let me draw it. So basically I'm just running down these backwards. So x and y, x goes to y. So that's traveling along this one. And then y goes to x, so that's traveling along this one. And y goes to z, so that's traveling along this one. So f reverse is a perfectly healthy set of pairs, but it's not a function, right? You see this? It's not a function. Or you see this? Y is getting associated to x, and it's getting associated to z. So this thing cannot make up its mind as to where y should get sent to. If I input y, it does not have a well-defined output. Should it be x? Should it be z? The answer is it's nothing. You cannot evaluate this at y or anywhere for that matter because it's not a function. So a perfectly healthy set of pairs, but not a function. So in this context, I would say that while f is a function and f reverse is a perfectly fine set of pairs, it is not the inverse of f. I would say f has no inverse. For f to have an inverse is for the reverse of f to be a function. Then that would be called the inverse of f. So this is just one picture with one example, but it's very telling. What happened? Why is it that when we mirrored this picture and flipped it around horizontally, we ended up with something that's not a function? Well, the bad part about this picture here is this, right? One dot with two things. Sorry, it's kind of flipped. Okay, it's hard to gesture because the camera looks flipped around to me. But because of this, one dot with two things coming out of it on the left side, right? That makes it not a function. There's one input is trying to get associated to two different outputs. That corresponds to this output having two inputs associated to it, right? X and Z. So what do we call this situation? This is f. This is a picture of f not being injective, right? Not being a one-to-one function, not being injective. So this is non-injectivity. So what we're seeing here is that what causes f reverse to not be a function is f not being injective. And actually, if you go back and you look at not the definition of injective, but down here, this equivalent way of stating injectivity, to say that f is injective is to say this. And if you look at this, this is just one pair flipping away from being the definition of being a function, right? So if you just flip these pairs around, then you've got basically this, right? Just the variable names have to be replaced. That's fine, they're all bound variables. But basically, injectivity and functionhood, this here under definition 48 and this here under theorem 58, they're just the same statement but with the pairs getting flipped around. So that's kind of the observation we're making here in this picture. So then we can describe when is f invertible. When is the reverse of f a function? It should be when f is injective. And here it is. That's our next theorem, theorem 72. If you have f a known function, then f is invertible. In other words, f reverse is a function if and only if f is injective. All right, so I'd like to prove this theorem in the lecture, but I'll make it part of the optional part of the lecture. So the official core important parts of the lecture end here with this video, and in the next video, if you want, you can view a proof of this. Either way, whether, well, if you don't watch the video, then definitely read and study the proof of this on your own, at least.